Hi, my name is Young Cha. I will present our paper titled Mobile Egocentric Human Body Motion Reconstruction using only eyeglasses-mounted cameras and a few body-worn inertial sensors. We envision a convenient 3D telepresence system available anywhere, anytime, without relying on any instrumented environments. Such a system requires sensors embedded in commonly worn items, such as eyeglasses, wristwatches, and shoes. To this end, we present a wearable 3D capture system relying only on eyeglass-mounted cameras and inertial measurement units on wrists and ankles. Our egocentric system reconstructs the wearer's motion using learning-based pose estimation and retargeting a human body model. The reconstruction is transmitted to a remote person and shown on a VR display in real time. Our system is capable of reconstructing fast body movements indoors and outdoors and runs at 30 Hz. Working toward wide acceptability, we use an eyeglasses form factor for our headset and a reduced number of IMUs. However, the entire body is almost never captured due to self-occlusion or out-of-image situations. Using only sparse initial data is insufficient for estimating non-instrumented body parts. Prior visual initial fusion approaches can produce unreliable estimates for occluded joints and require more than 10 IMUs. In prior egocentric systems, the cameras are mounted further away from the face to offer better body visibility. Sparse initial pose estimation method suffer from pose ambiguity as multiple poses can be possible with similar measurements. As contributions, our system overcomes challenges such as inconsistent body visibility as well as insufficient initial data. Our proof of concept prototype enables self contained egocentric reality capture at any location in an unobtrusive eyeglasses form factor. Our reconstruction pipeline takes synchronized visual and inertial data as input and consists of three stages. In the first stage, the visibility over network estimates the 3D positions of visible joints while suppressing unreliable occluded joints. The detections from two egocentric views are merged and then transformed to word space using the headset pose estimated from Visual Slam. In the second stage, the 3D orientations of IMU instrumented lower bones are estimated using visual and inertial alignment in bone direction space. The temporal orientation network estimates the orientations of uninstrumented upper bones using a sequence of previous estimates. In the third stage, using the estimated joint locations and orientations, the shape and pose of the parametric body model are estimated. I'll go into details in the first two stages. Stage 1. The 3D joint network outputs joint coordinates, depth maps, and confidence maps. The network is trained with the joint visibility. When the joint is visible, the losses are applied for coordinates and depth maps. For invisible joints, the heat maps are forced to be smaller to encourage node detection. In stage 2, the raw initial measurements for lower ones are refined by visual inertial alignment at runtime. The IMU offset matrix represents a sensor misalignment from the visual coordinate space. The rotation offset is updated whenever new visual detections are available, so that all prior visual inertial bone direction pairs agree with the offset. Instead of solving for all available pairs, we cluster the directions online for efficiency. The uninstrumented upper bone orientations are estimated using a sequence of inertial lower bone features and visual upper bone observations. The visibility constrains the output orientation to be inside or outside camera field of view. Using the features from last 20 frames, the network estimates the upper bone orientations. None of the existing datasets includes both egocentric and inertial data, so we collected a new human pose dataset for training and evaluation. We also annotated joint visibility into three categories: visible, occluded, or outside from egocentric views. We evaluated our method on EgoVRP dataset with the baseline approaches. Our method shows significantly better and stable pose estimates for occluded or outside joint situations. The methods are evaluated on every joint position and orientation letters in three joint categories. In all categories, our method significantly outperforms both visual-only and inertial-only methods. The hours 8 IMU shows the best performance because all bones are instrumented with IMUs. However, the accuracy of our sparse IMU method is comparable while using only 4 sensors. We demonstrate an interactive physical therapy application in VR. The remote trainer provides real-time audio feedback.
Awesome. Now let's try some yoga stretches to warm up. Sweet. That was great. How about some jumping jacks next? Some squats and lunges, maybe?
We also demonstrate our system outdoors using a backpack PC. Wearing the backpack, the user performed standard soccer exercises in an area of about 50 square meters. The visual slam and the joint detections are shown on the top corners. In conclusion, we presented the Egocentric system that works with sparse visibility and sparse inertial sensors. In the future, as cameras and items become smaller and embedded into personal items, we expect convenient mobile telepresence to become commonplace. Thank you.